Alrighty, folks, welcome to week 13, day 1. We're going to be moving on to our next unit today. We're going to be working with antiderivatives, okay? You can pretty much use some context clues there. We're going to be doing the opposite of derivatives while we are looking for an antiderivative. Okay, so our essential question is, how would you find the original function given the derivative, in this case, y prime is equal to 3x squared? So essentially what we're trying to do is we're trying to do the opposite of what we did prior. Now, we know that there are a number of ways to find derivatives. We can have derivatives using the power rule. We've got the product rule. We've got the quotient rule. And we've got chain. Now, these are our 4 typical ways that we've talked about throughout this year to be able to find derivatives. Today, we're going to be primarily focusing on undoing the power rule. Okay, this is going to be our main objective today. Okay, so oops, clear that. Okay, so the first question that we're going to have here is you need to do the opposite of the power rule. So essentially, if we're given that y is x cubed, we know that from the power rule, we're going to get our derivative. It's going to be 3x squared. So you can also think of it the opposite way. Essentially, if y prime is equal to 3x squared, then y has to be equal to x cubed. Okay, if you wanted, you could think of it like brown. So we're going to have y equals x cubed. You bring this down, you get y prime is equal to 3x squared. So essentially, we're just doing the opposite of what's going on here. Okay, so this general process is known as finding the antiderivative. In any case, the y prime is going to be 3. If it's 3x squared, our antiderivative is going to be x cubed. But the question here is this going to be our only answer? I think it helps to look first at these 2 functions here. Now, if we're looking at the function, oops, let me move that out of the way. We're looking at the function y is equal to x cubed plus 2. Then we're going to find that our derivative here is going to be 3x squared. We're looking at the function y is equal to x cubed plus 8. We're going to get that our derivative here is going to be 3x squared. Now, both of these get the same derivative, but they represent 2 different functions. So essentially what we're looking at here move to the next page. When we take an antiderivative, we have to also include a constant c. Now, this constant c can be anything. In our next talk, we're going to figure out how to find specific values of c. But in our case, when we're finding a general antiderivative, anytime you have y prime is equal to 3x squared, for an instance, we're going to get that the actual function is going to be x cubed plus c. Now, this constant c can represent any number. Okay, so we need to make sure that anytime we take an antiderivative, we're going to be adding that constant c there. So first example here, we're going to find the general solution of the differential equation. So we're given that our derivative is y prime equals 2. Now, the first thing we have to do is we have to find a function whose derivative is going to give us 2. Now, I hope that by now we can all realize that y is equal to 2x. It's pretty much going to be our only function that's going to give us a derivative of 2. To find our final antiderivative, though, all we're going to do is add the constant c. So we're going to get y is equal to 2x plus c. And this is what we're going to be looking for. Okay, this is the general solution of the differential equation that gives you y prime equals 2. So we're going to talk a little bit about notation now. Now, notation for antiderivatives revolve around this differential equation. Now, this chunk right here should look familiar. Okay, there's one thing that it's missing though. I hope we all can see it. It's missing its prime. Okay, so typically we would like to think that dy dx is equal to f prime of x. When we're going to be talking about this kind of format though, we're just going to refer to it as f of x. We'll see why in the next slide. Okay, so essentially we've got dy over dx is going to be equal to f of x. And all we're doing here is we're multiplying by dx on both sides to get that dy is equal to f of x times dx. Okay, again, we'll talk about on the next slide on why it's f of x and not f prime of x. It's just general notation here. Come on. Okay, so previous notation, we're able to find a general operation. Now, the operation of finding all solutions of this equation is called an anti-differentiation. It's denoted by an integral sign. Now, this sign right here, okay, you'll see it hundreds of times moving forward. It's going to be this weird, long-looking f without the line in the middle. This is known as an integral. We're going to be talking about integrals for the remainder of this unit. Okay, now this is our general solution. So if we have y is equal to the integral of f of x dx, this is going to be equal to our function of x plus some constant. So essentially what's happening here is we're taking, so the original function y is going to be equal to the anti-differentiation of our derivative times dx. Okay, so f prime of x, known as our integrand, is essentially our derivative. Okay, this is f prime of x. Okay, it's just how the general formula is denoted. So f prime of x dx, if you take the integral of it, you're going to get your original function. Okay, so it represents the antiderivative, what you're looking for, and then we're still going to add that constant c. Okay, again, this is just notation. Something I want to make clear though, this dx is super important. You cannot take an integral if it's not in respect to a variable. So in the case where you have a derivative in terms of x, you have to include this in your integrand. Okay, you cannot take an integral without some kind of dx, dy, or something in there. Okay, it has to be in respect to some certain variable. Okay, so we're going to have a couple basic integration rules here. The first one we're going to look at is going to be the integral of 0. Okay, the integral of 0 dx, now we should think of it as taking an antiderivative. So any value that gives us a derivative of 0, we should all know what this is. It's our constant. Okay, this is just going to be c in the case because we don't actually know what this value is going to be. Anything that has a derivative of 0 is just some number. Okay, as I stated up here, so k represents a constant. So for our next one, we're going to take a derivative we're going to take an integral of just a number. Okay, so k represents a number. This can look like an example here of 2 dx. So 2 is our derivative, dx is in respect to what variable, and we're taking an integral of this function. So we need to find our antiderivative. In this case would be 2x, and then we're going to add our constant. Okay, now that's for a specific example. I want to make sure that we have our general formulas here. So anytime that we have k dx, we can actually rewrite this as kx plus c. So anytime you have just some number here, it's going to be written, its integral is going to be kx plus c. Now the next one, the notation is a little bit funky, but there's a general rule that we're allowed to do. Anytime that you have some number we're actually allowed to pull it out. Okay, so we're going to have, I just started doing 2 again. Do that. So we're going to bring our k, which represents just some value, and we're going to have an integral of f of x dx. Okay, so again, anytime that you have some kind of constant, you're allowed to just bring it out. So say, for example, we had the integral of, let's say, 3x. Okay, so essentially, or dx, essentially what this is going to be is we're going to be able to take this 3 out. So we have 3 times the integral of x dx. Okay, let's go ahead and actually, yeah. And then we're going to go ahead and say that this is going to be 3 times x squared over 2 plus c. Okay, the integral of x would be x squared divided by 2. Bring that 2 down. There we go. Okay, this is essentially what we're going to do here is anytime that you're adding or subtracting functions within an integral, you're allowed to break it up into multiple integrals. So in this case, we're going to have the integral of f of x dx plus the integral of g of x dx. Okay, a nice little example of this would be if we had, let's say we had the integral of, say, 2x plus 5x squared dx. Okay, we're allowed to rewrite this as the integral of 2x dx plus the integral of 5x squared dx. Okay, so pretty straightforward so far. Get this out of the way. Last one here, anytime that you have a function x of n and you're taking the integral of it, it's a nice little trick that we're going to have here. It's going to be x to the n plus 1 over n plus 1 plus c. Okay, so this is made evident in the example I did right. Come on, where'd my pen go? Right over here. So notice I have x to the first power here. So you would add 1. So 1 plus 1 gives a x squared, and then 1 plus 1 over 2. So anytime you have x to some power, it's the integral of it is going to be x to the n plus 1 over n plus 1 plus c. Okay, moving forward. Okay, so we're going to do a couple of specific examples here. So we're going to take the integral of 1 over x cubed dx. Now this looks a little bit ugly at first. We're going to keep this in a couple different steps. The first one's we're going to rewrite it. Now we're going to rewrite it so that we're not dealing with fractions. We don't like fractions. We don't want to work with them right now. So we're going to have the integral of x to the negative third dx. Okay, from there, we're going to integrate it. And this is essentially our x to the n power. So we're going to use that rule we were just talking about a second ago. We're going to have x to the n plus 1, negative 3 plus 1 is negative 2. And it's going to be over n plus 1. Negative 3 plus 1 is going to be negative 2. And we cannot forget to add our constant. And then this last step here is we're going to simplify. Okay, in this case, there's not a lot to simplify. We're going to have negative 1 over 2x squared plus c. And this is going to be our definite integral. Okay, so definite integral is the term that we're going to be used when we're describing finding an integral. Okay, so we're going to do the same process here for this next one. First thing we're going to do is we're going to rewrite it. So we're going to have integral of x to the 1/2 dx. We're going to integrate it. Okay, so add 1 to 1/2. We're going to have x to the 3 over 2. And it's going to be over 3 over 2. Now, I know a lot of us are not super comfortable with dividing fractions. Don't forget to add our constant. So this is the same thing as x to 3 over 2 divided by 3 over 2 plus c. So we have x to the 3 over 2 multiplied by 2 over 3 plus c. And our definite integral is going to be 2x to the 3 over 2 over 3 plus c. And that's what we're looking for. Okay, so again, first step is to rewrite it. We don't want to work with a radical just as much as we don't want to work with a denominator. So rewrite it so that we just have one exponent. Then we can use our rule where the integral of x to the n is equal to x to the n plus 1 over n plus 1. So we get x to the 3 over 2 divided by 3 over 2. And then you just simplify. Okay, moving along, we've got, I believe, 4 more examples. Okay, so integrate the polynomial. Now in this case, we don't really have a polynomial. Now, anytime that we don't see something, we're going to go ahead and imagine that there's a 1. So this is the same thing as the integral of 1 dx. Now remember, we can go ahead, pull out a constant. It's just the same thing as right there. So essentially what we're going to get, the derivative or the antiderivative of 1 is just going to be x, and then you have to add your constant. Okay, so that's all we're getting there. The antiderivative of 1, so the opposite of the derivative, would just be x, because if you took the derivative of x, you would get 1, and then you add your constant. Okay, moving on to our next one here. Okay, so we're going to integrate the polynomial here. So in this case, we have an addition. So since we have an addition, we're allowed to split this up into multiple integrals. So we're going to go ahead and split this up into the integral of x dx plus the integral of 2 dx. Now again, we're allowed to pull a constant out. So we're going to have the integral of x dx plus 2 times the integral of dx. Now we just talked about the last one where the integral of dx was just x. So we already know that 2 times x plus c. Okay, and over here, we're going to have the integral of x dx. Now this is just x to the first power. So we're going to go ahead and get, this is going to be x squared over 2 plus c. Now in this case, we're going to go ahead, or let's go ahead and simplify this first. We get x squared over 2 plus c plus 2x plus 2c. And if we wanted to simplify that one more time, we get x squared over 2 plus 2x plus 3c. Now, the next thing we're going to talk about here is we don't actually need 3 c's. We don't know what that constant is, so that constant can just remain a singular c. So our definite integral here is actually just going to be x over 2, x squared over 2, plus 2x plus c. Okay, even though you end up with 3 c's, that doesn't change what that constant is going to be. So we're not actually going to worry about that 3 at all. We're not going to worry about this. Okay, again, this 3, it does not matter that it's there. We're only going to write one singular c in our answer. Okay, 2 more examples here. Okay, so we've got a couple things we're going to do here. First off, there's a subtraction and an addition, so let's split this up into 3 separate integrals. So we're going to have the integral of 3x to the 4th power minus the integral, these all have dx's on them, by the way, minus 5x squared dx plus the integral of x dx. Okay, so let's pull out some constants. So we're now going to have 3 integral of x to the 4th dx minus 5 times the integral of x squared dx plus the integral of x dx. Okay, from here, we're now going to start taking our integrals. So we're going to have 3 times 4 plus 1 is 5. So x to the 5th over 5 plus c. Then we have minus 5 times 2 plus 1 is 3. So x cubed over 3 plus c. And then we have plus, this is to the 1st power. So 1 plus 2, or 1 plus 1 is 2 over 2 plus c. Okay, so we're going to go ahead and distribute and combine our like terms. I'm not going to worry about the c's because we're just going to have one c at the end. So I have 3x to the 5th over 5 minus 5x cubed over 3 plus x squared over 2 plus c. So this is going to be my indefinite integral. Okay, so that's the integral that we are looking at. It's known as an indefinite integral. Okay, it's an indefinite because we do not have a value for the c. For us to have a definite integral, we would have to have a value here that we could find something for. Okay, moving on to our last example here. This one, okay, this one's gonna look a little bit gnarly here at first, but we're still gonna do all of the same exact steps. First thing we're gonna do is we're gonna rewrite it so that we're not working with any denominators. So I'm gonna go ahead and split this up to be the integral of x over root x dx plus the integral of 1 over root x dx. From here, I'm going to go ahead and simplify it so I don't have any fractions. I'm going to have the integral of x to the 1/2 dx plus the integral of x to the negative 1/2 dx. And from here, I'm just going to do the same exact process I've been doing. Okay, so I'm going to add 1. I'm going to get that this is going to be x to the 3 over 2 divided by 3 over 2. We're going to add c, and then right here, we're going to have x to the 1/2 divided by 1/2, because negative 1/2 plus 1 is 1/2, plus c. Okay, I'm going to go and start simplifying these. This right here is going to give me 2x to the 3 over 2 divided by 3. This piece right here is going to give me 2x to the 1/2. And then again, I don't have to worry that there's 2 c's. I only have to include one of them in my final answer. So my indefinite integral here is going to be that value right there. And yeah, thank you very much, folks. That's the end of my video.